So inside a capacitor, we have this electric field. And when I say inside, I mean between the two plates. We've just been looking at parallel plate capacitors that have just two metal plates separated by some distance d, and they've got some potential difference that we're calling V between the two. And really, it's a delta V, but convention is just to use a regular V, with no delta. I mean, so we'd have positive charges on one side and negative charges on the other, and then the electric field inside between those two plates, it turns out is going to be pretty much just straight lines going across from the positive end to the negative end. And it turns out that it's uniform, that we have the same strength of electric field here as we do over here and here and here and here, and everywhere between those two plates the electric field has the same strength, or very, very close to the same strength. Now, how strong is it? Well, we have an equation to help us with that. The average electric field between 2 points, whether we're talking about a capacitor or not, is equal to negative V over D, where V is the voltage and D is the distance, or the separation between those plates. We'll measure that in meters, and we'll measure this one in volts, and then E average is volts per meter, or newtons per coulomb. Those units work out to be equivalent here. So if we got the voltage for this capacitor, or the potential, the change in potential between these two plates, and we know how far apart they are from each other, we can figure out what the average electric field is too.